Welcome back. In this lesson, we're going to look at the sun. Don't look at the sun very long, or it'll burn your eyes out. But we're going to study what the sun is, what it's made of, how it works, how it gives energy, and in terms of all of the energy in the earth, it's always traced back to the sun. What we need, it's providing in terms of energy. So we'll look at a lot of the details. All the other stars in the galaxy, our sun is rather small. It's actually a middle-sized, smallish middle-sized star. In terms of our solar system, that sun is almost all of the matter that's in this region of space. So it takes up about 99% of all the mass in the solar system, with all of the planets and all of the moons and the asteroids and the comets and everything else that's in the solar system making up the final 1%. The sun is essentially a furnace. It is a nuclear furnace in which gases, very light gases, hydrogen if there is any, will be pressed into larger atoms. So the gravity of the sun is so big because of how big it is. So if you were to give just an idea, you can put 11 Earths along the diameter of Jupiter, and you can put 10 Jupiters along the diameter of the sun. So it's roughly 110 times bigger than the Earth along the diameter. So it's a massive object. Even though that it's very light, the sun could float on a lake if you had a big enough lake. Of course, I think the fire would probably put out the water, but the density of the sun is very, very light because it's made up of very light gases, much lighter than, say, water. Its temperature is enormous, about 1 × 10⁷ Kelvin. That's 10 million Kelvin. Ridiculously hot in the center. It's much less on the surface, but the center is where the nuclear explosions are happening. So when you think of a hydrogen bomb is essentially happening inside the sun continuously, and then that energy is coming out of the sun. So the sun is burping out all kinds of atomic nuclei that's being forced together in the center. Also electrons, as essentially you have a plasma gas going on in the inside of the sun. The outer part of the sun, I guess, is called the atmosphere, even though that it's gas all the way to the inside. The very final layers of gases are called the atmosphere of the sun, and there are a few. Most of the ones on the very outside are invisible, so the corona can't be seen. The upper and lower chromosphere cannot be seen. Normally, when you simply look at the sun, you can't see that part. The part that you can see is called the photosphere, and the photo means light. So the light you can see of the sun is from the photosphere. The these upper layers of the sun are a little much cooler. The upper atmosphere can be 10,000, and then the corona can be 1,000,000 Celsius. So it's very, very hot. So there are layers. You wouldn't think that they would all be one temperature, but it isn't. There are layers of hot and cooler areas in the sun. So we said that the photosphere was the part you can see. It's the one that's burping out visible light. All of the sun is emitting all the electromagnetic spectrum. So radio waves and gamma waves and microwaves and X-rays, all of that's coming out of the sun, along with heat and along with the visible light that you can pick up with your eye. So the chromosphere, the two layers of the chromosphere and the corona can only be seen during an eclipse. So if the moon were to pass its shadow along the earth and block out the center of the sun, and the moon is properly positioned so that the entire moon would be the size of the sun at that distance, which is unbelievable that if you were think of coincidences, that moon is just exactly the right size so that when it passes through, it becomes the size of the sun that's much farther away. It's a much bigger sun, but it's much farther away, and those two at the different scales are exactly the same size. So when the moon passes across and it completely takes away the surface of the sun, the corona is now visible, which is this crown-looking rays that if you've ever drawn in kindergarten a sun and you have the rays coming out from the sun, that's the corona of the sun. So here's a picture of the corona. People who have seen eclipses have no idea of just what they're looking at until it actually happens, because they can't imagine just how cool it is. So this, which normally is obscured by the light coming from the photosphere, is basically backlit by the sun, and the sun is being shielded by the moon. So it's just a remarkable event, and people love it. People will actually fly to other places that are having eclipses because they can't get enough. The solar wind is essentially what's coming out in the corona. It's ions, it's stuff that's being burped out of the sun, and it's coming at huge speed towards the planets. So, for instance, what we call the auroras, the northern lights and the southern lights that you find in the very far north, very far south of the planet, is caused by the solar wind. The solar wind's particles, the ions, these positive and negatively charged particles that have been broken up by the sun's eruptions, is being bombarded into the Earth, and the Earth has a magnetic shield, and the magnetic shield is caused because the inside of the core of the outer core of the Earth is made out of magnetic metals like iron and nickel, and it's molten and spinning, and that spinning metal gives a magnetic field. The magnetic field then deflects these ions that are coming out from the sun and diverts them to the north and the south. And so you end up with the auroras happening only in the far north and far south. Without the magnetic field, you wouldn't have the auroras, but you would have all the danger that those ions would happen as it encountered the Earth head on. The solar activity, there's all kinds of things to see. Essentially, you need a few terms. When you have a loop, like here in the picture, where essentially you've got this ions and energy that's coming out that is being controlled by the magnetic field of the sun, because the sun is also spinning, and all the ions that are spinning is causing a magnetic field in the sun, and these magnetic properties will either push or pull these ions out of the sun as they're exploding outward. So you can get these beautiful flares and loops and prominences, which are some people just find fascinating to study. So it's kind of like a bed of lava, if you want to think of it as exploding lava, but it's all in gases. It's ionic gases, which is called plasma. Now, because of these magnetic properties, some parts of the sun emit hotter and some emit colder. Now, the colder is not sending out as much light because there's not as much energy coming out at that area. And so these cold spots on the sun are called black spots and or sunspots. A sunspot essentially is a brown or a dark spot on the surface of the sun caused by these magnetic fluctuations inside the sun's boiling surface. And some of these spots are very, very big. So several of them are the size of the Earth, and one of them in particular is the size of Jupiter, which is about 10 or 11 times the size of the Earth. So there is a kind of a fluctuating cycle of sunspots. So they will rise and fall because, remember, the sun is creating these fields because of its spin, and it's very regular. So about every 22 years, you're going to get an increase in sunspot activity, and then a decrease, and then an increase. And as it's going up and down, the general trend can go up and down. So where you can have very low sunspot activity and very high sunspot activity that can correspond with the weather. And we've studied this already in terms of sunspots causing the changes in climate in the past. More recently, there is a scientist that studied a very low sunspot activity from about 1600 to 1750, and it correlates with the founding of America and immigration from Europe and all kinds of things that were happening, because what's happening when you have very low sunspot activity tends to have very cold climates in that region of the space that's facing the sun at that time. So if the northern hemisphere is in summer during that time, then that summer's going to be colder than normal. If the southern hemisphere were farther away, then you're going to even get colder than normal temperatures in the winter. But it's more pronounced in the summer because the things that would have grown in the summer didn't quite grow as well. And so you can kind of trace this historically, which I think is pretty fascinating. We mentioned some of the prominences and the flares and arcs. So a flare is basically being burped out of the sun, exploding out of the sun with the material that's coming from it, the ion specifically, and other parts in the solar wind. That prominence is that arc that we saw before, where the magnetic fields are pulling and pushing the erupted material out of the sun. Frankly, the sun's interior is just gravity on gases. These gases are pulled in so tight together that the nucleuses that normally repel, so if you have positive nuclei, they will repel other positive nuclei. Opposites attract, like charges repel. So one atom doesn't like to go into the space of another atom. They're almost like two cars that don't want to share space. So if they crash, they're going to buckle, and a lot of times the bigger one will bump the smaller one away, and that's exactly what happens with atoms. If you have extremely intense pressure that gravity would cause in the case of the sun, then what happens is that the nuclei actually go so close that they get pulled in together. And instead of two protons in two different hydrogen atoms, you'll end up with one helium atom with two protons in it together. So those two protons are essentially pressed in to make a new nucleus. And in that way, lighter atoms are giving rise to bigger atoms. Bigger atoms are created as a result of the sun's activity with a huge amount of energy. I guess the formula that most people have heard of, they may not know what it means, is derived from Einstein, and the big E is energy. The M is some kind of matter, so it's the mass of some kind of a matter, and the speed of light is that c squared, the square of the speed of light. So the square of the speed of light is just a number, it's a constant, so it's not going to change. What this is meaning is a little tiny m times a very big number of speed of light gives you a lot of energy. So the energy contained in a teeny tiny little bit of matter is enormous. So when those two atoms will fuse together, you're going to get a nuclear explosion that is seriously high emitting of energy. And that's what's causing the sun. The solar energy is caused by fusion of two of the hydrogen atoms as they're pressed together. So the energy is sent outward from the sun. Okay, so as it goes out, you're going to have it in a complete sphere, and we're only getting a little bit of that, whatever is touching the Earth. Okay, so it becomes about 1,333 watts per square meter. So the energy, if you have a 100-watt light bulb, then you can have 1,300-watt light bulbs being energized just by the sunlight that falls on one little square meter, a meter on each side. So that's how much energy is coming from the sun all the time over the entire Earth. You're going to see it's more intense towards the middle and less intense towards the edges because the Earth is not flat to take the full direct sunlight, but it's curved and so you end up with some temperature deviations that causes the seasons. The spectra is showing you that it's not just one frequency of energy. These frequencies of energy go all the way through, and so what we see as a rainbow is just the spectra of energies that our eye can pick up. The low energies would be red, the high energies would be purple, and it goes through all of those colors. Well, if you think of what the sun is not just emitting light, it's emitting all of the electromagnetic radiation, which is a continuous spectrum. Now, in this picture, I've got the continuous spectrum, which shows the rainbow, and then an absorption spectrum, which shows a couple black lines. And what you'll see is that every element is going to give a specific fingerprint, either by very bright lines at certain frequencies or dark lines at certain frequencies, where those frequencies are actually absorbed by the hydrogen, or absorbed by the helium, or absorbed by the nitrogen, or whatever it is that is there. And so you can look at a star, and by the fingerprint of these black lines or bright lines, you can actually determine what gases are in that star, what's being burned as fuel, which is pretty cool. So these are called spectrums, and the absorption spectrum is based on every single element specifically. So the sun spectrum is showing you some black lines at various places. So there is more than just helium here. There's hydrogen here. There's helium. There's other larger elements in the sun, but there's mostly hydrogen. And so every fingerprint, there's a specific fingerprint for every element, and then you simply overlay one fingerprint on top of another, and you can kind of backtrack that to find out what frequencies are being shown up. So what are the elements inside the sun? What has the sun produced from hydrogen, pressing it together into something big, and the hydrogen that's burning?